In this video, we will be analyzing one of the control methods that could be used to monitor the everyday task of driving a car. The main goal when driving a car is to control its position and velocity. We assume that the only components of the car that can affect these parameters are the steering wheel and the gas and brake pedals. While the steering wheel only affects the position of the car, the gas and brake pedals affect the velocity and therefore the position of the car. In our scenario, we will assume that we are driving in a flat, straight road and that we are doing so in the most efficient way possible. So, the brake pedal will not be used. Our goal is to keep a constant distance from the car in front of us, and we will achieve this by using only the gas pedal.
The person driving is a key component of our dynamic process, and for the control method we will discuss further in this presentation. As seen in the diagram, the car will be the plant, for it consists of the process and an actuator. In our case, our car needs to be a distance x behind the front car, and any deviation from x is considered an error. The person will visually determine if the current distance is the distance desired. Based on that analysis, the person determines the amount of pressure needed on the pedal to either maintain the desired distance or the amount of pressure needed on the pedal to decrease the error and reach the desired distance. As you can see, the gas pedal will be directly related to the velocity of the car. As we will explain in the next slide, the pressure applied to the pedal will coincide with a specific angle of the pedal.
In our car, just like in any other car, the gas pedal has a maximum angle theta where it will start at and always return to. We will call this angle theta naught. A change in theta will result in the car speeding up to reach the velocity associated with that change in theta. At this point, if theta remains constant, the car will travel with a constant velocity. But if there is a change in theta, the car is subject to speeding up or slowing down. Thus, the angle of the pedal is proportional to our velocity. This image shows part of our open loop system if we were to code it in Simulink. Here, our input will be the new theta we are at, and the output of the transfer function will be our velocity. Our transfer function will be a low-pass filter since we are assuming that we are driving effectively and only expect smooth theta changes.
Here, we add an integrator to our open loop. This turns the velocity into position, and this position is relative to the distance desired. Now we have our closed loop system. We add a sum block which determines the difference from the desired location and our actual location. This is our error. We also add a PID controller which allows for an error approximation of 0. This is what allows us to reach and maintain our desired distance. We can tie it all together now. We first determine our desired location. Then we press the pedal, which results in a new angle theta, which in turn is our input. We then pass the angle through a transfer function which produces our velocity. Finally, we integrate the velocity through the integrator to find our current position. This position is then compared to our desired position and we get the error from the sum block. This cycle continues on, ensuring that our error is always approximately 0.